Hi, welcome to Math 389, Advanced Analysis. So this is lecture 8. And so what I want to do is I want to continue one of the problems we were discussing before about whether or not a solution exists. And then I want to move into handling one of the requests from somebody in the class about problem solving and fun problems to look at. And so I want to try to find a way to work that in. And so I will hopefully do this in a way you have not seen before. So the first is, we talked about the beautiful Baker-Campbell-Hausdorff formula and do the coefficients exist? And so we said, well, let's look at, say, e to the, I think we did ax, e to the bx, e to the z of xy, or maybe c. I think we'd probably use the letter c of xy. And the question was, will there be some answer for c that works? And so on this side, it's going to be I plus ax plus a squared x squared over 2 factorial plus dot dot dot. And then we'll have I plus b y, oh, that should be a y, plus by plus b squared y squared over 2 factorial plus dot dot dot. And then on the other side, it's the nightmare. I plus c xy plus c xy squared over 2 factorial plus dot dot dot, where c xy, we were trying to figure out what's the best way to write it. Write it maybe as I plus some matrices. So we'll have something in x plus something in y plus something x squared plus something xy plus something y squared plus dot dot dot. And the question was, when we put this in, will we always be able to solve and determine what these unknown matrix coefficients are? We need to figure out what goes in these spots. And we did enough in the previous class to show that we could at least get the linear and the quadratic terms to work. And what's nice is when we are looking at what's going on, let's see, wait, does c of xy have an identity, or is it no identity? It was no identity, right? It was just starting off with this term, right? Yeah. So when we look at c of xy to the first power, it's going to contribute linear terms, quadratic terms, cubic terms, and so on. When we look at cxy squared, it's going to contribute quadratic terms and higher. When we look at cxy cubed, cubic terms and higher. So at least if we only care about terms of degree 5, nothing of degree cxy to the 6 and higher can contribute. So we can reduce things to a finite problem, and we can pick off the coefficients one by one. We showed how to do the linear and the quadratic. Now, if we want to do the cubic, I guess I'll add one more term here if I want to do the cubic. So we'll have the cxy cubed over 3 factorial plus dot dot dot. If we want to get a cubic term, we get pieces from cxy and cxy squared and cxy cubed. But by induction, by previous work, we already know the linear and the quadratic pieces from cx and cxy. Those have been the linear and quadratic pieces on cxy have already been forced on us by looking at the linear and the quadratic. We have never used any cubic part of cxy in just matching up the linear and the quadratic. So the cubic terms in cxy are completely free. When we look at how do we get a cubic term, well, the cxy in the beginning is going to give us cubic terms. The cxy squared, that will give us cubic terms, but none of those cubic terms will come from the cubic terms of cxy. They'll come from just the linear times linear, linear times quadratic. And the cxy cubed, we'll get it from linear times quadratic, or linear times linear, I think is the only way we can get it. And so what's nice is if we're looking at the cubic terms of cxy are completely free in the cxy piece And then we have all this other crap coming from the other pieces. And then we have the cubic terms on the left-hand side. So we have enough freedom to know that we will be able to choose the cubic terms of CXY. So something exists. And now that we know the cubic terms, now we can look at the quartic terms. And so the method will work. Now, two big questions remain. One question is, what are those coefficients? Can you write down a nice formula? And then the second is, does the sum converge? Maybe the resulting expression doesn't converge. So it'd be horrible. The hope is it's an exponential function. There hopefully is enough convergence with the factorials that we should be okay. But this hopefully shows you that the method will at least determine the coefficients uniquely. And we'll just keep ticking them off one at a time. If you want, as some practice, you could consider, say f of x is the sum of an x to the n, g of x is the sum of, say, bm x to the m, and look at f of x, g of x, call that h of x, is the sum of ck h to the k. Can you find formulas for the ck? This isn't too bad. And you can always gather data. It's a0 plus a1x plus a2x squared plus dot dot dot. B0 plus b1x plus b2x squared plus dot dot dot. And when we start multiplying things out, the constant term is just going to be b0 a0. The x term is I could have a1 b0, or I could have a0 b1. If I want to get an x squared term, I could have the a2x squared hits b0. So it's a2 b0 plus a1 b1 plus a0 b2. And hopefully the pattern is clear. So in this case, ck would just be ak b0 plus a k minus 1 b1 plus dot 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 plus a0 bk. Or if you wanted to do it more formally, just the sum L goes from 0 to k of a k minus L BL, which makes sense. If I choose x to the k minus L from the first, I have to choose x to the L from the second. So here's an example where I can easily write down what the coefficients are. Okay. Next one is the coefficients of the inverse. So let's say I have, no problem. So let's say I have, what we're doing right now is we proved that BCH will work, that you will be able to explicitly find coefficients. We did not prove that there's a nice formula for them, and we did not prove that the resulting sum converges. And then on the next one, we just showed that if I give a product f of x times g of x, there's a very simple formula for what the coefficients are for the product. Yep. And so now we're doing the inverse. So if f of x is the sum of an x to the n, and g of x is the sum of, say, bm x to the m, if f of g of x equals g of f of x equals, so what should it equal if I want f and g to be inverses? It should be x. What are the b's in terms of the a's, or vice versa? So do you think we should be able to come up with the series expansion for the inverse? In principle, if I give you f, should g be determined? Yeah, it's the inverse of f. Okay. Now, how would we find that? Any thoughts? And I don't care if it's pleasant. I don't care if it's easy to do. If I want to factor a number, I could just try all the numbers less than it and see what goes in. And as a theoretical mathematician, I now have a factoring algorithm. My computer scientist friends will laugh at me, but I have a factoring algorithm. Can you give me an approach to find the B's in terms of the A's or the A's in terms of the B's?
Start matching the code to the constant vector, then match the.
Yeah. So G of f of x is going to be B0 plus B1 f of x plus B2 f of x squared plus B3 f of x cubed plus dot dot dot, and that equals x. Right? So what can you tell me about B0? So therefore, B0 equals 0. Similarly, what could you tell me about A0? Why? By symmetry. And A0 equals 0, looking at f of g of x equals x. This is just going to hopefully help me simplify things a little bit. So if I want to have f and g going in this direction, I need b of 0 and a of 0 to be 0. Okay, so now I have b1 f of x, that's going to be a1 x plus a2 x squared plus dot dot dot, plus b2 a1 x plus a2 x squared plus dot 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 squared plus b3 a1 x plus a2 x squared plus dot 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 equals x. What's the only way I can get a linear term?
B1 and 1x.
Yeah, so when I look at this, I'm going to get a b1 a1x. That's the only linear term. How can I get a quadratic term?
B1 A2
I could have b1 a2
plus B2 A1.
b2
Yes.
a1 squared. And then this would be a cubed over here. So, and this should be a dot dot dot. So that's the only way I can get an x squared. What about the cube term? I'm clearly going to have a b1 a3. From the square factor, if I want to get a cube, I could have a1 times a2 or a2 times a1. So I think it's going to be plus 2 a1 a2 with a b2. Or for the next one, for cubic term, I could have, I think, a b3 a1 cubed. Yes? So what do we know about b1a1? 1. So b1 equals 1 over a1. What about this? What does that equal? 0. Will we be able to solve for this? So can we find b2 in terms of the earlier b's and the a's? So we're assuming we know the a's. Does this give us b2? Yes. So, whoa, sorry. So gives b2 in terms of a's and earlier b's. What about this expression? Does this give b3 in terms of the a's and the earlier b's? So in principle, this should work. What's the one thing we have to be careful about?
Is it true that some of it, some of the A's could be zero, so then you can't have like one.
So which is the only A that would be bad for us to be zero? A1. Could A1 be zero? No. So if A1 is zero, then B1 can't be 1 over A1. The function is not invertible if A1 is zero. If you think about it, if you start off with the function as something x squared or x cubed or x to the fourth, it shouldn't be, a nice one-to-one function. And so because the coefficient of B2, B3, etc., is just powers of A1, you're okay. So note A1 does not equal 0 as invertible, so can find the B's. So now you can ask, is there a nice formula? And it looks like there might actually be a nice formula. And then the question becomes, if I give you a nice series expansion for F, is there a nice series expansion for G? Will the resulting sum for G converge? Just because I can write down what the coefficients, B's are, doesn't mean the resulting sum converges. And so I'll leave this as a somewhat open problem, if you want to just play with and get a feel for, okay, in principle, this will tell me that the B's will exist. Will the resulting sums converge? And if so, for what region? But hopefully this is enough detail for you to be convinced that we can pick off these coefficients. And the idea is we pick them off one at a time. And this is a real common technique in analysis, is we reduce it to, I've got my next term free, and I can express it in terms of the previous stuff. Now that I know that, I then move to the next term, and that introduces a new free parameter, which I then solve using the earlier stuff. And I just keep doing it one at a time. All right. So what I want to do now is I want to talk about sums of powers. And the motivation for this was to try to talk about tricks. And there was a request to talk about tricks, and so I want to do tricks. So the most famous trick goes all the way back to Gauss. And the story is that he was around 5 years old, he was in school, and the teacher just didn't want to deal with the brats. And anybody who's ever taught knows what this is like. I don't even want to think about how many decades it's been. I still remember the day in second grade when we had 5 recesses. And I didn't realize until years later, the teacher just couldn't deal with us that day. I just kept sending us out onto the playground to just run around. 5 recesses. I mean, it was amazing. So the teacher said, add the numbers from 1 to 100. And so what Gauss noticed is if you take the numbers from 1 to 100, or since we're mathematicians, we'll do 1 to n, or 0 to n, and you write them backwards, then when you add them every time, you get n. And so if we call this sum Sn, then we know that twice Sn is just n plus n plus n, n plus 1 times. So 2Sn is n plus 1 times, or Sn is n plus 1 over 2. Beautiful trick. What you would love to do is now use Gauss's trick to evaluate the sum of squares, or sums of cubes, or sums of fourth powers. But we can't do that. Right? Or can we? Well, what would we do if we had sums of squares? So 0 squared plus 1 squared plus n squared. If we tried to write it backwards, we would have n squared plus n minus 1 squared. And then let's look at some kind of general term. So I'll slide this off a little bit. And we'll have the general term would be maybe plus k squared plus n minus k squared. And so we need notation. So the notation Sn is actually bad notation. So maybe let's make the notation a little bit better. And again, this is where it's nice to be able to just erase. Let's call this maybe S1 of n. Because now, very easily, I can just say this is just S2 of n. Do we get anything nice when we do this? So if we add, we get twice S2n over here on the right. What would we get on the left? Yeah, the first term would be n squared plus 0 squared. The next term would be n minus 1 squared plus 1 squared. N minus k squared plus k squared. And then plus all the way down to 0 squared plus n squared. What's n minus k squared plus k squared? So n squared minus 2nk plus 2k squared. So if we think about this, we would sum this, k goes from 0 to n. This is the same as the sum, k goes from 0 to n of n squared, minus 2n, the sum k goes from 0 to n of k, plus 2, the sum k goes from 0 to n of k squared. Do we know what the first sum is? So this is n squared times n plus 1. Do we know what the second sum is? I'm sorry? 2n times n plus 1 over 2.
Oh, yeah.
Right? We know what that is. And what about the last one? Do we know what that sum is? That's S2n. And what does this whole thing equal? I'm running out of space here, so I'll write over here. And this is just equal to. So how many of you were optimistic for a moment? No one was optimistic that this was looking good, that we were going to get an S2n. We were going to be able to solve this. We were going to be able to extend Gauss. What do you notice about the gold and the green? They cancel each other out perfectly, and we get 2s2n equals 2s2n. What a shame, right? This is similar to like the bring it over method in integration, where the idea is you have this integral that you don't understand, you do some manipulations, maybe you integrate by parts twice, and you get the integral back again, but with a coefficient in front of it that's not 1. So then you can bring it over to the other side, and you get this multiple of the integral that you don't know equals something that you know, you divide by that coefficient, and now you've solved it. And so it was looking promising that we might be able to, sneak out a formula for the sums of squares, but sadly it perfectly cancels and we have nothing. Oh well. How would you normally prove a formula for this? induction. The problem with induction is you need to know what to prove. And there are advanced high-level ways to find out what you should prove. Okay, so what I want to do now is 1 plus 3 plus 5 plus ... plus 2n minus 1. Does anybody know what the sum of the first n odd numbers is? It's n squared. Does everybody agree that you could prove this by induction if I asked you? Okay, so I'm not going to ask you. Here's the geometric proof. 1. What's the next odd number? 3. The next odd number? 5. The next odd number? And you can see that as I go from one level to the next, and then there's one dot here, the corner dot actually goes to 3. So that's why you have 2 more dots in the next level. So each level is 2 dots more than the previous. And you can see that it's in a square grid. So the sum of the first n odd numbers is going to be n squared. So is everybody comfortable with the sum of the first n odd numbers is n squared? Okay. Well, if instead of asking you to sum the odds, what could I ask you to sum? Evens. So what would 2 plus 4 plus 6 plus 2n equal? N squared plus n. Because each term is 1 more than the corresponding odd, so it's just n squared plus n. What if we add these together? What do we get? So if we add, we get 1 plus 2 plus 3 plus 4 plus 2n minus 1 plus 2n is n squared plus n, whereas 2n squared plus n. So 1 plus ... plus m equals, let's let m equal 2n, is going to be 2n squared. So if m is 2n, n is m over 2. So n squared is m squared over 4. So this is going to be m squared over 2 plus m over 2, which is m plus 1 over 2. Did we just prove our formula for the sum of the first m integers? So did we just prove the sum of the first m integers is m plus 1 over 2? Nope. What's the subtle mistake? So this is m is even. Okay, so let's fix it. So we know we could look at, I need another color. There's another color. So need to do m equals, say, 2n plus 1 is odd. So we could do 1 plus 2 plus ... plus 2n plus 2n plus 1. Well, that we can do. That's going to be n squared plus n squared plus n plus 2n plus 1, which is going to be 2n squared plus 3n plus 1. And so now, let m equal 2n plus 1. So n is equal to m minus 1 over 2. Figure out what's the best way to do things. So we have a 2n squared. I want to replace this in terms of n, in terms of m. How should I do this? So we could, So we could factor this as 2n plus 1, n plus 1. And if we do it like that, the 2n plus 1 is just m. So we get this is m. And now how would you write n plus 1? So we know m is 2n plus 1.
Why can't we just plug it in minus one?
So that we could get m minus 1 over 2 plus 1.
Yes.
And that gets you m minus 1 over 2 plus 1. Well, the plus 1 is plus 2 over 2 becomes m plus 1 over 2, which is now m plus 1 over 2. And there's the formula. So we've now proven the formula for the sum of the first m integers just by knowing that the sum of the odds is the first, k odds is k squared by geometry. So I don't know if anybody's ever made this argument before of using knowledge of the sum of the odds to get the sums of everything. There's definitely been arguments like this in mathematics where you use one set of values to get the other. And so frequently, for instance, if you know the sum over the evens is twice the sum of everything, but to half the level, right? If I know the sum of the evens, 2, 4, 6, 8, etc., if I know those terms, if I divide everything by 2. So there's lots of tricks like that. A famous formula is the sum of 1 over n squared, n goes from 1 to infinity, is pi squared over 6. And so if I want to, this is the same as the sum 1 over n squared, n is even, plus the sum of n odd, 1 over n squared, is pi squared over 6. Well, if n is even, this is the same as the sum, m goes from 1 to infinity, 1 over 2m squared, plus the sum n odd, 1 over n squared, is pi squared over 6. Well, this is just 1/4 the sum m goes from 1 to infinity of 1 over m squared, plus the sum n odd of 1 over n squared is pi squared over 6. But this is just pi squared over 6. So we get that the sum over the odds of 1 over n squared is just pi squared over 6. We subtract it off, so we'll get 3/4. Or if I've done the algebra correctly, I think you just get pi squared over 8. So this is a nice trick where by knowing the sum over everything, we could actually deduce the sum over the odds trivially. And so this is a really common theme going from one sum to another. Okay. All right, so let's do Fibonacci's. So I will define it so f0 is 0, f1 is 1, f2 is 1, f3 is 2, f4 is 5, and in general, fn plus 1 is fn plus fn minus 1. Has everybody seen the Fibonacci's? Okay. So let's let Sn be f1 plus f2 plus ... plus fn. Anybody know what the sum of the first n Fibonacci's is?
Fn plus one.
It can't be fn plus 1.
Yeah, it's more than that.
It's more than that. So let's try to calculate a few. So the Fibonacci's are 1, 1, 2, 3, 5, 8, 13, 21. So let's calculate, n and Sn for a few values. When n is 1, we get 1. When n is 2, we get 2. When n is 3, we get 4. When n is 4, we get 7. No. Yeah. I'm sorry? So 5. Would be 9 or 12, I thought. Oh, for 4?
I think it's 7.
It's 7. 1 plus 1 plus 2 plus 3. And for 5, what do we get? We just add 5, so it'd be 12. For 6, we add 8, we get 20. For 7, we add 13, we would get 34. I'm sorry, 33. Does anybody notice these numbers? 1, 2, 4, 7, 12, 20, 33. Do those look like any nice numbers? So the Fibonacci's are 1, 1, 2, 3, 5, 8, 13, 21, 34. Our sequence is 1, 2, 4, 7, 12, 20, 33.
I'm just
Some index to F
minus 1.
-1. So F7, so when n equals 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like it was the 9th number -1. When n was 6, it looks like it was the 8th number -1. Looks like it was the 7th number -1.
It's almost like a sum of exponential powers of 2.
Almost, but not quite, because it's not growing that rapidly.
Yeah.
And I know you know that it's not growing that rapidly. So this is the advantage of data, is by looking at some data, we can make some conjectures. If you're proving something by induction, it is so much easier if you know what you're trying to prove. There's a great website, the Online Encyclopedia of Integer Sequences, the OEIS. If you have a string of integers, you feed it into the OEIS, and it tells you all the places it knows where they arise, and it knows many places where they arise. We now have a conjecture. What's our conjecture? Sn is Fn plus 2 minus 1. Do you think you can prove this by induction? Yes, because we now know what to try to prove, right? Proof by induction. The base case is easy. Inductive step. If we have F1 plus Fn, and then we add the next term, by induction, this is Fn plus 2 minus 1. We're adding, oh, that should be n plus 1, Fn plus 1. Oh, and Fn plus 2 plus Fn plus 1 is just Fn plus 3. And so knowing the conjecture, the induction becomes extremely straightforward. What if we didn't know the conjecture? So again, this is a class that has no class needing it as a prerequisite. We have freedom to do whatever we want. So when you send me emails of what you're interested in, I will adjust the lectures accordingly. The goal was to show techniques and tricks. So I now have to show another way of evaluating the sum. So looking at the sum of the first n Fibonacci numbers, does everyone agree that that's a little hard? I'm going to show you an easier sum that we can do. I'm trying to think if I prefer odds or evens. Let's start off with evens. F2 plus F4 dot 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 plus Fn minus 2 plus Fn. Let's sum the first n even Fibonacci numbers. I claim that it's actually not that bad to sum the first n even Fibonacci numbers. What does F2 want to be added to? F3 is one possibility. What's the other possibility? F1. So if we add 1, what would we get? So if we add 1 to F2, what do we get? F3. And now F3 plus F4 gives us F5. We have an F6 over here, so that will give us F7. We march down. We'll have a Fn minus 1 with an Fn minus 2. Oh, so this would be an Fn minus 3. That will give us a Fn minus 1. And when we add that to Fn, we get Fn plus 1. So this even sum has to be Fn plus 1 minus 1. So does everyone agree that it's actually not that bad to sum the even Fibonacci numbers? All right, what if we gave the even indexed, sorry, the even indexed Fibonacci numbers, not the even Fibonacci numbers? What if I gave you the odd indexed Fibonacci numbers, F1 plus F3 plus F5 plus F7 plus dot 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 plus F, maybe 2n minus 3 plus F 2n minus 1.
Subtract the total. Sorry, subtract this from the total.
We could. Is there anything nice we could add to F1?
0.
I'm sorry?
0.
So if we add 0, what would we get? We would get F2. So let's add 0 and we get F2. What's F2 plus F3? It's just F4. F4 plus F5 is F6. F6 plus F7 is F8 plus dot dot dot. F2n minus 4 would become F2n minus 2, and then that would be Fn minus 1. Sorry, 2Fn, no, minus 1. Okay, so here is where I might have done things a little bit. So I switched notation. And so I used n as a generic thing in the top where n was even, and in the bottom I used it as I explicitly wrote the odd numbers. I apologize. So if I want to try to make things consistent, I can drop the 2's. Let me just fix all the indices. And so I'll just assume n now is odd in the bottom one, and we'll figure things out later. And then this would be n minus 2. This would be n minus 3. This would be Fn minus 1. And then this would just be Fn. So in the top, n is an even number. And in the bottom, n is an odd number. So can we now figure out, the sum of all the Fibonacci? So again, we have to be a little bit careful with odds and evens. So if I give you F1 plus F2 plus dot 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 plus F2n minus 1 plus F2n, I can write this as F with the odd indices plus f with the even indices. And so now if I do the even indices, oh, sorry, if I do the odd indices, I get, I think, Fn. And then the even indices, I would get Fn plus 1 minus 1. And then that should give me Fn plus 2 minus 1. And then you just have to play games with, what if I'm not going to an even number? What if I'm going to an odd number? That's not too bad. But this idea of if I can understand a simpler sum, can I understand the more complicated sum? There's actually something to this. And so if people looking for something to write up, you have this trick of understanding some of the sums and then passing to the others. We can do this in a lot of cases. And again, it's which things seemed easier or hard to you. Looking at this, to me, looking at the sums over the even or the odd indices wasn't so bad, because I know if I just add a little bit, like a domino effect, they're going to just keep combining and pushing down. Whereas if I have the sum of everything, it's not so clear what it is. Now, if you write and gather data, which is one of the things I want all of my students to master, gather data, especially in the 21st century, write some code, calculate things, see if you can detect a pattern. Once we have the pattern, the induction is trivial. If you don't have the pattern, it's much harder. And so the question is, would you be able to solve this problem if you didn't have the pattern? It all comes down to looking at things right. This is why I was talking about the Rubik's Cube earlier today. You hold this one at the 30-degree angle, it's trivial. What's the right way to look at these problems? And so this leads to, I think I left a lot of space. Okay, sums of powers. Okay, sums of powers. So does everyone agree that if I'm kind and I want to do 0 to the k plus 1 to the k plus dot 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 plus n to the k, this is some polynomial in n of degree k plus 1? How many of you have seen this before? Good. I don't think you've seen this before. You've seen this for small k. If k equals 1, it's n plus 1 over 2. If k is 2, it's n plus 1, 2n plus 1 over 6. If n equals 3, it's n squared, n plus 1 squared over 4. But it's true, but it's a lot of work to prove this. If I tell you, so we'll call this pk plus 1 of n. If I tell you pk plus 1 of n, can you do the induction? Yes.
Do you think it's possible to do the sum using like the Bell summation?
So how would you do that?
Just separate each term as like n to the p minus 1 times. I'm not sure. And then if we already know what
So that's definitely worth trying. So you would write this as a product of two sequences.
Right.
And then you would need to know partial sums.
Right.
And so the question is, would you get something nice at the end, or would it reduce to what we had before? We had twice S2 of n equals S2 of n.
Right.
So absolutely should try. So the Abel summation formula, the reason I'm not doing it right now is because I always get it slightly wrong if I have to do it on the spot, is let's say I'm looking at, AM, BM, M goes from 0 to K. Oh, sorry, 0 to N. Is this AN B0, BN minus A0 B0? And then plus the sum, M goes from 0 to N. Is it then capital A of M? I'm sorry?
Is it minus that or? Oh, maybe depending on your sign for the piece.
And then you're going to have B M plus 1 minus bm, or do I want it the other way?
I think the other.
So bm minus bm plus 1? Yeah, because you have some freedom in terms of which way, where am is little a 0 plus a1 plus dot 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 plus am. It's the sum of, it's the partial sums. And so the problem here is if you try to do Abel summation, you need to know what the sum of a is.
Oh, some of these. Okay, that's.
Well, if am is the k minus first power, then capital A would be the kth power. And that's what you're trying to solve for. But maybe what you could do is maybe you could have am is m to the k minus 2, and maybe bm is m squared. And now when you're summing capital A, that would be a lower power.
Right.
But you're going to be having, so it's absolutely worth trying to see if you can make this work. You might be able to. You might have trouble if you let a and b m to the k minus 1, because then that's immediately putting into things that you want to know, and then you're summing the things that you want to know. But if I only go to the k minus second power, then I might be okay. Does everybody agree, though, that if I tell you what pk plus 1 is, you can do it? And you even have some thoughts about pk plus 1. Because we know, what's pk plus 1 of 0? If I take n equals 0, what does the sum have to be? 0. So the constant term is 0. And we know 0 to the k plus dot 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 plus n to the k is approximately the integral from 0 to n of x to the k dx, which is x to the k plus 1 over k plus 1 at 0 and n, which is n to the k plus 1 over n, over k plus 1. So the leading term has to be 1 over k plus 1 x to the k plus 1. So in terms of what the polynomial is, we actually have some idea. If it has to be a polynomial, it's got to be degree k plus 1. We know the leading term. We know the constant term. What we can then do is we could then evaluate it at a bunch of n's and then find by interpolation what's the only polynomial that works, and then prove by induction. So we could evaluate for some n, find the only poly that can work by interpolation, and then solve by induction. So if we believe it's a polynomial in n of degree k plus 1, we can figure out what that polynomial is by just evaluating it for like k minus 2 or k minus 1 choices of n. Now that we know the polynomial, now we can do the induction. But that requires you to evaluate it each time. There are methods involving Bernoulli polynomials and whatnot that allow you to do stuff like this. What I want to do is I want to introduce a new method to try to attack a problem like this. All right. So imagine, let's just quickly review. Everybody should know the geometric series. And let's say I give you 1 plus x squared plus x to the n, and I'll call that Sn. If I multiply by x, it should be clear that you should subtract both sides. And then you would get 1 minus x times Sn is 1 minus x to the n plus 1. So Sn is 1 minus x to the n plus 1 over 1 minus x. And then the typical geometric series formula is if the absolute value of x is less than 1, and then as n goes to infinity, this goes to 1 over 1 minus x. And you can view this as 1 over 1 minus x to the n plus 1 over 1 minus x. So as n gets very, very large, if x is less than 1 in absolute value, the second piece is becoming negligible. Everybody's comfortable with geometric series. Okay. What I want to do is I want to differentiate, and I want to switch the order of a derivative and a sum. Should you be worried? Yeah, right? When is the one time I can easily interchange a derivative and a sum? Finite sum. So a finite sum, I can do things. So let's consider, so we said, let's say Sn of x is 1 plus x squared plus x to the n. Do we know what that equals? Yeah. That's just 1 minus x to the n plus 1 over 1 minus x. Let's take the derivative with respect to x. Okay. And there's two ways to do this. I could just take the derivative, or I could take the derivative and then multiply by x. Okay. So when I do that, I would get, x, Sn prime of x is going to be 0. What's the derivative of x with respect to x? And then I multiply by x, so I'm going to get 1 times x. X squared, what's the derivative of that? 2x, and I multiply by x, so I get 2x squared. All the way down to n times x to the n. And now I just have x times the derivative on the right-hand side. Who remembers how to do their quotient rule? Yes, you should all remember how to do the quotient rule. Who would use Mathematica or Wolfram Alpha or something like that to actually do the derivative? Me. You would still do it by hand? Or some of the program? Yeah, I could do it by hand as well, but I would still plug it in. So it's f prime g minus fg prime over g squared. So the g squared is no problem. I'll do that. 1 minus x squared. All right, your turn. All right, the derivative of 1 minus x to the n plus 1 is going to be negative n plus 1 x to the n, and I multiply by 1 minus x. And then I have minus 1 minus x to the n plus 1. And what's the derivative of 1 minus x? Negative 1. Okay. So we've got 0. If you want, I can write 0x to the 0 plus 1x to the 1 plus 2x squared plus dot 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 plus nx to the n. Oy boy, okay. So when you look at it, I've got x. I'm not going to spend too much time making things nice. I'll have a negative n plus 1 x to the n 1 minus x. Minus and a minus becomes a plus 1 minus x to the n plus 1 over 1 minus x squared. This is true for all values of x. Anybody have any thoughts about a good value of x? 1. Why would you take x equals 1? Yeah, so x equals 1 gives the sum of 0 plus 1 plus n. So all I have to do is plug in 1 on the right-hand side. You don't look happy.
But wouldn't that not work for the denominator?
So, okay, yeah, that's bad. What about, so the denominator blows up. What about the numerator when x equals 1? Well, no, it doesn't blow up. Technically, the denominator doesn't blow up. The denominator is 0, which causes which tries to make things blow up. But the numerator is also 0. What can we do? L'Hopital, right? We did L'Hopital illegally earlier in the semester. Now let's do it legally. Do I have to worry about the x outside? We all agree that when x goes to 1, this factor of x outside is just 1. So L'Hopital, you know you've made it when your name becomes a verb. So this would just be the limit as x goes to 1. And so when we use L'Hopital, how do we evaluate? What do we do? Differentiate. So the denominator becomes 2, 1 minus x. See, I'm doing half the work. And the numerator, I'm sorry? Oh, with a -2. Thank you. I'm not doing half the work correctly. Okay. Now for the top, we could use the product rule. It's actually better to expand things first. -n+1 x to the n minus x to the n+1. And its derivative is going to be -n+1, and it's going to be n x to the n minus 1 minus n+1 x to the n. So rather than using the product rule, it was better to expand. So I like to say Henry David Thoreau is the patron saint of mathematics, with his command from Walden, simplify, simplify. Before you do some algebra, stop and think if this is the algebra you should do. So now when we plug that in, the derivative is going to be a -n+1. Then we'll have an n x to the n minus 1 minus n+1 x to the n. And then the next term is going to be a minus n+1 x to the n. What's the denominator? Still 0. What's the numerator?
Oh,
Also 0. So notice in the numerator, both factors have an n+1. We can pull that n+1 outside. They both have a negative sign. We can pull that outside. So at x equals 1, the numerator is -n+1, and then it's going to be n minus n+1 plus 1. And what does that equal? 0. What do we do? L'Hopital again. Take the limit as x goes to 1. Do you agree that it's worth pulling out the -n+1? Yes? So now, what's the denominator? Do we agree the denominator is just 2? The numerator is going to be n times n minus 1 x to the n minus 2 minus n+1 times n x to the n minus 1 plus n+1 times n x to the n minus 1. Is this okay now as x goes to 1? Denominator is now fine. So now we get -n+1 over 2. And when x equals 1, okay, let's see. We have an n minus 1, an n+1, an n minus, an n+1 times n. Okay, everything has an n. So can we just pull out an n? Sure. So it's -n+1 over 2. And then the first piece is going to just be an n minus 1. The next piece is going to be a minus an n plus 1. And the next piece is going to be a plus. Did I make a mistake? Oh, wait, I put out an n plus one, so wait a minute. There shouldn't be. I can't pull out, I'm sorry, I put out the n plus one earlier, okay. So we had n minus one. We had n plus one times n. Oh, we had pulled out the n plus one. There shouldn't be an n plus one here. Okay, so I had made a mistake. Okay, there we go. So this is the correct thing now. When x equals 1, do we still have trouble? Okay, sorry, yeah. This is the problem when you try to do too much algebra at once. So let's pause and let's just take the expression and just start doing the algebra again. So that's the only way we're going to be okay. So do we agree that we have this? And this is the same as n plus 1 times the limit as x goes to 1 of -2, 1 minus x. We will pull out a negative n plus 1. So we're going to have n x to the n minus 1 minus n plus 1 x to the n plus x to the n. Oh, we could actually simplify that a little bit. The negative cancels with the negative down below. We'll have n plus 1 over 2. We have the limit as x goes to 1. Now we have n x to the n minus 1. We have a negative n plus 1 x to the n, and we have a plus x to the n. That's just going to be a minus n x to the n. And then the denominator is just 1 minus x. I'm sorry? What cancels? Right, so we can pull out an n. We'll have n plus 1 over 2, the limit as x goes to 1 of x to the n minus 1 minus x to the n over 1 minus x. And then as you're noticing here, we could use L'Hopital, or we could notice that we can pull this out as a 1 minus x. So it's n plus 1 over 2, limit x goes to 1. I can pull out an x to the n minus 1, and I get 1 minus x over 1 minus x. And so I don't have to do L'Hopital again. And what do we get? n plus 1 over 2. We proved the sum of the first powers of the integers is n plus 1 over 2 by using L'Hopital. Now, there was a reason I used the operator x d by dx. Because when I did that, I kept the power of x the same. If I were to do this again and apply x d by dx, I would get x, and then I would have x Sn prime of x derivative. I would get 0 plus 1 squared times x plus 2 squared times x squared plus n squared times x to the n. And that would just be x d by dx of what we had before. So I actually did this calculation years ago in a paper that I wrote on elementary ways to evaluate these sums using L'Hopital. My challenge to you is, can you use this to prove that it must be a polynomial of degree k plus 1 in n? So can you prove you get a polynomial of degree k plus 1 in n when do 0 plus 0 to the k plus 1 to the k plus n to the k? So we know that it has to be something. Is it possible that when we keep doing L'Hopital that it always blows up? Could it always blow up with L'Hopital's rule? I know I'm going 1 minute over. If you have to leave, that's fine. Why not? Yeah, the left-hand side is finite and nice. So I know if I keep using L'Hopital, eventually it's got to be nice. So I can't remember if I did this in the paper or not, but can you try to prove that you will get a polynomial? And then based on what we've been talking about, the last question is, let's assume you're able to prove it's a polynomial. Can you say anything about what those coefficients are? This is a constructive method to find the polynomial for any k. You give me k equals 50, I just do it so many times, I keep doing L'Hopital, I expand everything out. It's completely deterministic. There's no trying to find small values and build it together. But can you extract a useful formula? This is the difference between proving something exists and finding a way to calculate it. So this is another one of the problems I really love. It's a nice technique, but to get something useful from this, to figure out what those coefficients are. So keep sending me what you're interested in. I will keep trying to work that into what we're talking about. I really want to go over different techniques and what you can do with them. All right, so this is a good place to stop.